So welcome to the 8th video of this course, a crash course in quantum processing. Today is the delving more into the classical coding. Last time I talked about the operator sum representation that will be useful for quantum error correction. But let's first with the classical coding, how we can write a code in classical information theory. Let's recall that I have here a number of bits that I would like to transmit from me to another person, let's say Alice and Bob, and the transmission channel is called a binary symmetric channel. So I transmit from Alice to Bob, or Alice transmits from herself to Bob through this channel, so this binary channel for logical zeros and ones. Let's recall if I have an error, this kind of probability to get the error is P. Okay, so if I transmit 1 and it will become 0, the probability to get error actually. So it's flipping means that error has happened. But for 0, let's say it's 1 minus P. 0 will transform to 0 by this probability, and 1 will transmit to 0 will be by this probability. For 0 to 1, if I have this kind of 0 to 1 will be P, and if I have for 1 to 1 is nothing than 1 minus P. So what if I try to write a classical code? How can we write a classical code in classical theory? So I can write it in terms of N, K, and D. Number of bits I have, I arrange them by number of strings. It will be 2K number of strings. So we will take an example, but just to put ourselves into the pinpointing exactly what classical coding is. So n raised to k will get me number of n-bit strings that I have, and d is what I call Hamming distance, or minimum Hamming distance that I have here. That I have XOR, if I say distance for x and y, and w is this is the weight. This is what I call the weight for x ORed with y. Weight actually number of bits or number of ones that I have. So let's take an example. If I have 3 ones, okay, and I'd like to write them. Here I have number of strings that I have, n-bit strings. I have 3 bits, okay. For k, I have just one case for k, so it will be 1. Just one type of bits I have. For the Hamming distance, 1, 2, 3, I have also 3, okay. Let's write like this. And the same also for zeros. Okay. So let's take an example of a real error procedure that I have here. If I send 3 zeros to a receiver and it will be transmitted the 3 zeros, let's suppose it's the first case. So the first case, 3 zeros, I mean that I have probability of 1 minus P cubed, because 3 and this 1 minus P here, so 1 minus P cubed, and it will decode eventually 0, and maybe it will be received in terms of 0, 0, and 1, and the probability will be 1 minus P, but here 2 zeros square, and with 1 is P, and it also decodes 0 because number of zeros are much larger than, or even larger than 1. What if I have 0 and 1 and 0? So get me the same, decoding 0. What if I have 1, 0, and 0? It will get me P, the same. No, 1 minus P squared P, decode 0. So what if I have 0 and 1 and 1? And here comes the issue that I have error. So here is P squared 1 minus P, and it will decode 1. What if I have for 0, no, let's say 1, 1, and 0, so it will be the same, it will decode 1. What if I have 1, or maybe 1, 1, 1, so this will be P cubed, and it will decode 1. What if I have, we say 1, 0, and 1, and it will decode the same P square 1 minus P, and it will decode 1. So if I would like to measure the probability of getting the error, what I said before, it's equal to P. But here I find that 4 decoded ones, and this is actually corresponding to error. And if I would like to measure the error, or probability to get the error, I sum for all both these. So it's P cubed, and I have kind of 1, 2, 3, 3 of P squared, 1 minus P. And if I have P squared as a common factor, it will be P plus 3, 1 minus P. Wow, I have here P squared, so it's not just P. And from here I can conclude that this error procedure, this error protocol procedure here is more favorable than the other, just a simple P, because it gets me lower P. The probability here is lower than the P squared is lower than P, and this is valid. It means here this is a valid, favorable procedure to error correction. Okay. Next time we'll go into quantum coding, and we will write down this in terms of quantum information coding. Thanks a lot, and see you in the next video.